this video, I will briefly cover everything we have covered so far in the astronomy unit. This is just a review. This video should help you see how well you know concepts, see what terms you have memorized. It won't cover everything in detail that's going to be on the test. You will need to study your notes, study your flashcards, study everything you can to prepare for this test. Again, this video should not be your only study guide. Alright, so for this video, I'll be covering the heliocentric, geocentric views, everything you'll need to know for that part of the test. The nebular hypothesis, also cover why we have heavy elements here on Earth, why the solar system is structured the way it is with the rocky planets on the inner side of the solar system while we have the rock or gaseous planets on the outside. We'll cover the solar system size and scale. We're going to cover why there is life on Earth, and we'll also cover the Big Bang. Now, there won't be too much understanding in this video. It is just to cover the basic information and topics we have already covered. Alright, let's go ahead and get started. Alright, so we first talked about the heliocentric, geocentric views. You should have picked up that science is a way of knowing or understanding the natural world during this section. We started with a geocentric view. Now remember the term geo as in geology or geography. Geo means Earth. The geocentric view, also known as the Ptolemaic view because of Ptolemy, means that the Earth is at the center of the universe. Now this was a wrong theory, but we like to talk about it because it shows us very well how science changes, science adapts when new information comes in. So the main scientist for the geocentric view was Ptolemy. His mathematical calculations predicted the location of planets based on epicycles. Now remember, epicycles aren't real, these are fake. We learned this through observation and evidence, and we were able to say that no, the geocentric theory is wrong. Now, science changes, science adapts. When new information or evidence disproves a theory or hypothesis, it's time to revise that theory or hypothesis, or even make a brand new theory. Now, the heliocentric did just that. The heliocentric view, which means helio, means sun, was the Copernican view, or the heliocentric view. This put the sun at the center of the universe. Now, technically, that's not quite true because the sun is not the center of the universe, but that's what they thought at the time. It certainly is the center of our solar system. Now, the heliocentric view was published by Copernicus. The sun is at the center, basically because things work better that way. All observations seem to make more sense with the sun at the center. And along came Galileo after Copernicus' death, and Galileo was able to show a lot of its different evidence for the heliocentric view. One of those evidences were the moons of Jupiter. We call those the Galilean moons of Jupiter. Basically, the geocentric view said, hey, nothing orbits anything else because the Earth is so special that everything orbits around Earth. Well, Galileo was able to look through his telescope at Jupiter, and he could see the moons of Jupiter orbiting Jupiter. So the moons of Jupiter helped disprove that not everything has to orbit the Earth. Alright, the next thing are the sunspots. Sunspots help show the Earth or the sun was spinning. Showing that other things in the solar system that actually spin was helpful because the geocentric theory said Earth sits still. It doesn't spin. Why would things spin? That doesn't make any sense. Galileo was able to look at the sunspots, see that they were moving around the sun, all sort of in unison, indicating that this thing was spinning around on its axis, showing that, hey, if the sun's spinning, why couldn't we be spinning? Alright, now the phases of Venus. The phases of Venus don't just show light changing. A lot of you get hung up on that. You're like, well, the phase of the moon, I know what that is, and I know what phases of Venus is, so it must have something to do with the light. It doesn't. It doesn't have anything to do with the light. The light kind of helps tell us where it is relative to us, but what's changing here is the size of Venus. Because Venus, and these are actual photographs here that were taken and then put in this diagram, not to scale at all. But the phases of Venus show Venus is so big here. And then watch, as it moves in its phases, it gets tiny. It gets really, really small. It does this because it's not orbiting us. It's orbiting something else. It's orbiting the central star in our solar system. So the phases of Venus show the planets are orbiting the sun and not Earth. Next thing here, a lot of you got hung up on this one as well, the morning and evening star. This would be Venus here in the sky, very, very bright when she's really, really close to us. Mercury and Venus can't be seen in the night sky. You can't ever see them. And that's showing that they're not orbiting Earth. And that they actually have orbits that are closer to the central star than our own orbit. So the big picture here is science is a way of figuring things out about the natural world. Science uses logic and reasoning. Arguments in science are based on evidence, observations, and facts. They're not based on feelings. Science is constantly changing and revising. Also, science isn't the only way to learn and understand and discover things about the world. There are other ways of knowing and understanding the world that we live in. Religion's one way, art is another way, self-expression is another way. All of these ways are good and valuable in their own way. Science is just a different way to do that. All right, so nebular hypothesis is the next subject we're talking about. So the nebular hypothesis is the best explanation of how a solar system forms. It starts with a nebula. So a nebula collapses due to its own gravitational pull, and it starts to condense. As it collapses, it also starts to spin. When it's spinning, it's going to form two basic things. First thing here is that dense, hot, glowing object in the center called a protostar. Protostar, once it gains enough mass, will become the star eventually. And then all this junk around the star is called the accretion disk. You see this here, this spinning material here. This is what eventually the planets are going to form out of. You need to know this term, accretion disk, and you need to know that that's what the planets are going to form out of. So pressure and heat is going to increase in that central protostar. Gravity is going to be pulling the material inward, and eventually we have nuclear fusion beginning. Once we have nuclear fusion beginning, we have a true star. Oh, and the light goes on bright as day. Bright as day because it's the sun makes day. Anyway, nuclear fusion, if you don't remember, is when you have atoms that are crashing together due to high pressure and heat, and when they do, instead of bouncing off each other, they're actually going to fuse into larger nuclei, into larger atoms. So in this case specifically, what happens is hydrogen atoms are going to collide, they're going to crash together, and they fuse, they merge together, creating helium atom and lots of energy. And remember, hydrogen is the smallest atom that we possibly have. And when the hydrogen merge together, they make a bigger one. They make helium. So when this happens, when we have nuclear fusion in this star, it sends a shock wave out in all directions from this intense heat and energy. The shock wave blasts from this increase in energy. It blows out lighter materials like hydrogen, helium, water, methane, and more way out in the solar system. Smaller planets, like this little dude right here that you probably didn't even notice was forming there, these planets that are forming closer to the star have all the material that was near them in their orbit basically just blasted away from them. What ends up happening is these smaller planets, because they're smaller gravity, they actually can't hold on to this material as the sun's blasting this material off, and they end up just staying small, rocky, and dense. Now, in the outer stretches of the solar system, way out there, is where most of this material ends up. This is where the outer planets pick it up. They take these lighter materials, and so the outer planets end up being very gaseous, very massive, and with probably pretty small rocky cores. Now I say small, but they're probably about the size of Mercury or Earth or Venus, for the core with a huge amount of hydrogen and helium gases. Now, eventually, gravity allows most of that junk in the accretion disk to form into the larger objects. Most of that stuff gets cleaned up throughout the solar system, and what we have is a fully formed solar system. This is where the Nebular Hypothesis stops. This is the last step of it because the Nebular Hypothesis is the formation of a solar system. So we do not have the destruction of a solar system because the Nebular Hypothesis is how a full solar system forms. So how do we get heavy elements that make up Earth? Well, the Nebular Hypothesis is part of that, obviously. But if that nebula, the cloud that the whole entire solar system formed out of, was made of just hydrogen and just helium, we would never have ended up with a planet made of silicon, made of rock that we have now. We would have never had a planet that's made up with a bunch of water. We would never have formed life like we have. We would have never formed cars. We would have never made desks that you're forced to sit in for hours upon hours every day. So it all starts with a star. So in a star, remember that stars, just by the way they work, are natural atom or element factories. Stars fuse elements in their cores until they get to iron. Well, iron doesn't release any energy, so the iron cannot fuse. Because the iron doesn't fuse, it's not producing energy, and that star is going to collapse in on itself. When it does, we call that collapsion. Collapsion, I'm pretty sure that's not a word. They die and they explode in what's called a supernova. So all of these elements that were contained in this star, that the star has created over its lifetime, are scattered, blown out into the universe. Iron then now has the energy it needed to fuse into large elements like gold, platinum, gold, uranium, did I mention gold? Plutonium, and many more of the larger elements that we have on the periodic table of elements, and they fuse with the added energy of this supernova. And then we end up again with the Nebular Hypothesis. We end up with this cloud of dust and gas. It's probably been made up of like 2 or 3 different supernovas. Or more than that. I have no idea. I'm just making up numbers as I go. Gravity eventually clumps all that material back together again and starts the whole process over again to build a new solar system. That leads to larger elements. Silicon, rocks, uranium, being able to be on Earth. So the video we watched, remember it said that if you have a gold ring, make sure you appreciate it, because the gold in that ring was fused in a brilliant display of light in a supernova explosion. Alright, so the Nebular Hypothesis is basically the best explanation of how a solar system forms. What is the evidence for the Nebular Hypothesis? So evidence for that is planets have an orderly structure with rocky planets near the star and gaseous planets further out. Also, all planets orbit the sun in the same rotational direction and the same rotational disk. And that's because they be formed out of the accretion disk, yo. Pictures also help give evidence of the Nebular Hypothesis because we have photos of solar systems at different part in their formations. So we look out, we see solar systems fully formed. We look out and we see different parts of the galaxy, and we see nebulas that are glowing hot. We look at different places in the galaxy, and we see protoplanets forming around stars, cleaning up the accretion disk. Another evidence that we look at are the age of rocks. When we look at all these different types of samples, including meteorites, they're all about the same age. This suggests that they all started forming around the same time, because it makes sense that if everything's forming out of the same material, that they all start forming at the same time, because gravity pretty much works the same all over throughout the disk. So it doesn't make sense for different objects to have different ages. So wait, How do we know how old the rocks are? So remember that some rocks have radioactive elements in them, and we can use the predictable rate of radioactive decay, this term will be on the test, radioactive decay of elements, to be able to determine how old a rock is. Remember that some elements decay in what's called a half-life. As these elements decay and one half-life has gone by, we know how much time has passed. So how old is the solar system exactly? Solar system is about 4.6, 4.7 billion years old. So let's talk about solar system size and scale. A galaxy is a system of millions or billions of stars together with gas and dust held together by a gravitational attraction. Now the Earth is located in a smaller solar system with a medium-sized star, which actually is located in the Milky Way galaxy. So solar system is only a tiny blip in the larger galaxy. If we compare the size of the Milky Way galaxy with the size of our solar system, the size of our solar system is about 2 light years across, while the Milky Way galaxy is about 70,000 to 100,000 light years across. Now, let's talk about light year real quick so everybody remembers what that is. A light year is basically the distance that light travels in 1 year. So light, all light, whether it's microwaves or gamma rays or light waves, all travel at the same speed, which is the speed of light. And a light year is just the distance that light is going to travel in a year. So basically, if you send a message, a radio message or any other kind of message, at the speed of light, which is how fast it travels, it would take just as many years to travel as it is in distance in light years. So, for example, I got a photo of these two brilliant stars here. These stars are in a binary system orbiting each other. These stars are actually about 4 light years away. If we send a message to this star system, the Alpha Centauri system, it would only take about 4 years for that message to get there because they are 4 light years away. So in our solar system, we're talking about size again, so come back to size. The sun is the biggest thing by far in the solar system. It's about 99% of all of the mass in our entire solar system. Now, if you noticed, the planets just appeared on the screen. They're so small you probably didn't pick that up, so I'll flash it on and off here. Right here, this is about how big our planets are compared to how large the sun is. Now, for our test, you will not need to know all the special properties about the planets, but you do need to know approximate sizes. So, for example, if I have Jupiter here, you got to know that Jupiter is pretty much the biggest planet in the solar system. You should know that Jupiter is bigger than all of the other planets combined. Even though Saturn's pretty large, it's not very dense, so it's not very massive compared to Jupiter. You should know that Venus is about the same size as Earth. You should know that Mars is smaller, much smaller than Earth. You should know that Mercury is the tiniest planet of all. You should be able to tell me, you should be able to guesstimate Earth compared to Uranus or Neptune, how big it is. If I were to ask you a question that said, is Earth about the same size as Neptune? Is it 1,000,000 times smaller than Neptune? Is it 30 times bigger than Neptune? Or is it about 20 times smaller than Neptune? You should be able to pick from those options roughly how big Neptune is compared to Earth. Alright, so let's switch gears. Let's talk about why there is life on Earth. Why is it Earth so special, while the other terrestrial planets maybe not so much? So the number one reason here, we needed 4 reasons. One is the magnetic field. The magnetic field helps protect the Earth from CMEs, coronal mass ejections, also solar flares. So this is not just radiation. A lot of you are confused, but it actually is material, plasma, that's ejected out of the sun. Basically, the sun's just like belching on us, and it comes and it hits our planet. Without the magnetic field, it would hit our atmosphere, and it would start to strip away our atmosphere. So the magnetic field helps keep the Earth's atmosphere from being ripped off the planet, which is, bad if we ripped off the atmosphere, because then we wouldn't breathe and we would die. All right, so Mars and Venus actually lack a strong enough field to help protect them out in space. Second reason is the habitable zone, or the Goldilocks zone. The habitable zone is the location away from a star that is not too hot nor too cold for liquid water to exist on a planet. Now, you've noticed in quotes, if you notice, you saw that down here. That's in quotes because it's technically not the heat of the star we're worried about, but the amount of radiation from the star, the amount of light radiation that's hitting the planet. And we'll learn why that distinction is very important in a couple of months when we go over meteorology. If you look here, this is an example of a zone scale. It's not to size at all, but we have a star here. In this area here, it's way too hot. In this area in the solar system out here, it's a little too chilly. And right here in this green zone, that's what we're calling the habitable zone. That area is just right. So Earth and maybe Mars are the only planets in the habitable zone in our solar system. The third reason is that we have liquid water. So as far as we know, liquid water is necessary for biological processes. All life as we know it and how it exists needs liquid water to survive. Earth and Mars are the only planets of the 4 terrestrial planets, the 4 rocky planets, to actually have liquid water. Reason number 4 is our atmosphere. Our atmosphere is this bunch of gases that are held onto our planet due to our planet's gravitational pull. Our atmosphere helps filter UV radiation with the use of the ozone layer. Its thickness helps break apart meteoroids and asteroids. And the greenhouse gases that exist in our atmosphere, the very small, tiny amount that we have in the atmosphere, actually help it slow the escape of heat to space, keeping us warm at night. Now, Venus has way too thick of an atmosphere, and it's got way more greenhouse gases than we do. A lot more greenhouse gases than we do. So it holds on to its heat way too well. Mars has a very thin atmosphere, very much less gas molecules than we have. It does have a high percentage of greenhouse gases, but they're just not enough. There's just not enough material there to hold on to any heat, so Mars is very cold at night. So the Big Bang. Time to switch gears again. So now we're talking about the Big Bang. That's the last topic we're going to talk about today. What is the Big Bang? The Big Bang is a theory that is the best explanation for the beginning of the universe, how the universe began. It states that everything was once contained in a small point. We call this a singularity. Then a rapid expansion released energy and began space and time. From the energy, matter began to fuse, and eventually this created the first elements of hydrogen and helium. Hydrogen and helium clumped together and formed the first stars. And then the universe itself is still actually expanding today. It's still moving apart, stretching from that initial Big Bang expansion. Now, Doppler effect, we're going to dive into that real quick because that has to do with some of the evidence for the Big Bang. Recall, the Doppler effect is when an object is moving, its waves are actually going to be altered or changed. Now, here's an example of a chemical element. Recall that in the middle here, we have an example of an elemental signature. This is an absorption spectrum. Now, whatever chemical this is the same chemical here and the same chemical here. In the object here, this object is moving, this object is moving. Because these lines are all identical and evenly spaced apart from one another, we can tell that this object is actually moving because its color has shifted to the red end of the spectrum. This color has shifted to the blue end of the spectrum. It doesn't mean that it's blue or that it looks blue. It just means that it is moved closer this way. So let's say this object was a green object. It may look light blue now. If this object was a red object, it may look yellow now. Alright, so how do we determine if something's moving towards us or away from us? So when an object is moving ahead of you or away from you, it's actually going to become redshifted. Its chemical signature will all move or shift this way. When an object is coming towards you, it is actually becoming blue shifted. It's going to be moving to the blue end of the spectrum. The rhyme goes, red goes ahead, or I guess the saying, red goes ahead, blue comes to you. The evidence for the Big Bang Theory, one of the heavy evidences is the redshifted galaxies. When we look out into the universe, we see that almost all the galaxies are redshifted, and this tells us that they are all moving away, that space is expanding. Another one of those evidences is the CMB, the cosmic background radiation. This is basically the radiation left over from the Big Bang. We call this the heat left over from the radiation of the Big Bang, and we see it everywhere in space when we look. No matter where we look in space, we see this radiation coming from every direction, everywhere. Now, the last one here that we'll talk about in our class is the abundance of elements in the universe. With how much time has gone by, we should see a very small change in the amount of hydrogen to helium to other elements in the universe. And when we take observations of the universe, this is exactly what we see. We see a change of hydrogen to helium, showing that many stars have gone through. They have used up some of that hydrogen fuel. They have created helium. Some have created large elements from that helium, and we end up having about 1% of other chemicals, of other elements out in the universe, starting the Big Bang, having much less than that. So according to measurements, estimates, temperature, abundance of elements, and the size of the universe, how old is the universe? The universe is about 14 billion years old. Alright, that's everything for this unit. Hopefully you're studying your notes, you're studying your guides, you're studying your flashcards, and you are preparing well for this test. If it helps you, go ahead and listen to this video over and over again until you've got all those concepts down. Feel free to zoom in, zoom out, skip ahead, skip back, and get your studying on.